Assalamu alaikum students. I hope you all are fine. Welcome to another lecture of chemistry. I am your teacher Sumayya Khan. Today is the last lecture of this chapter, the long chapter chemical bonding. And today we are going to learn about covalent character in ionic bond and resonance. First let us see what is meant by covalent character in ionic bond. We have seen that the covalent bonds are the bonds that are formed by the mutual sharing of electron, whereas ionic bonds are the bonds that are formed by the complete transfer of electron between the atoms. Now, there are several ionic compounds which also possess partial covalent character, and they show properties which are similar to covalent compound. In our previous lectures, we have seen the ionic character or polar behavior of covalent character. So here you will see that there are ionic compounds which show or exhibit covalent character. Now lithium chloride is ionic, but it is more soluble in organic solvent than in water. We know that ionic compounds are easily soluble in polar solvents like water. But here it is said that lithium chloride, being an ionic compound, is more soluble in an organic solvent than in water, which is a polar solvent. Now, to explain the partial covalent character or the reason for this behavior, Fajans came out or put forth certain rules. Let us discuss these rules. Number one is the smaller size of cation and larger size of anion renders greater covalent character to ionic bond. It means that if an ionic compound is made between the cation and anion, in which the cation is quite small in size and anion is comparatively greater in size, that will render some covalent character to the ionic compound. Okay, so in lithium chloride, lithium is small cation and chloride is large anion, and lithium chloride is found to be covalent. Similarly, sodium chloride is also an ionic compound, but here the size of sodium is comparatively larger than the lithium. The anion is same in both these examples. Chlorine is present in lithium chloride as well as in sodium chloride. Okay, but the size of cation is different. Lithium is smaller and sodium is larger. So therefore, sodium chloride does not show greater covalent character as we observe in the lithium chloride. In the same way, in lithium iodide, the size of iodide ion is quite large. Therefore, lithium iodide is found to be more covalent in character than in lithium chloride, because here you can see the difference in the sizes of the anion. So when you discuss or take the example of smaller or size of the cation, how it affects the covalent character, you can take the example of lithium chloride and sodium chloride. And when you want to study how the size of anion can affect the covalent character in ionic bond, you can take the example of lithium chloride and lithium iodide. Now the second point is, greater the charge on cation, more is covalent character of the ionic bond. Okay, so if your cation is having greater charge, +1, +2, +3 like that, that cation will render more covalent character to the ionic compound. Here the example of aluminium trichloride, magnesium dichloride and sodium chlorides are given. In this example, you can see aluminium carries +3 charge, magnesium carries +2 charge, and sodium carries +1 charge. As the number of charge on the cation increases, the covalent character of this ionic compound also increases. This is what observed by the Fajan. So sizes of the cation and anion. Second, charge on the cation will render the covalent character to the ionic compound. What else? A cation with the outer electronic configuration of S2p6D10 type possesses greater polarizing power compared to the cation having the same size and same charge but having the outer electronic configuration of S2P6 type. This you will understand when you look into the example. The example of cuprous chloride and sodium chloride is given. Cuprous chloride is more covalent than sodium chloride. These two are ionic compound, but cuprous chloride exhibit more covalent character as compared to sodium chloride. In cuprous chloride, the outer electronic configuration of copper is of S2P6D10 type, whereas in sodium chloride, it does not contain d electrons, so it has only S2P6 type of configuration. Okay, now when this happens, the d orbital have very poor shielding effect and the cation experiences more effective nuclear charge. Okay, so in copper there is more effective nuclear charge as compared to sodium, and because of this greater effective nuclear charge, what happens, the cation becomes stronger and it will show more covalent character. Okay, so these are the three important rules put forth by the Fajans. How a ionic compound will exhibit covalent character. How we can explain the covalent character in ionic compounds. Let us come to the next topic, which is resonance. Now, many polyatomic molecules can be represented by more than one type of Lewis structure. Here the example of carbonate CO3 minus ion is given. Here it is printed wrong, okay? Now each of these structure, in these three structure you can see that the position of the atoms are fixed. All the carbon and oxygen are at the same place, but you will observe that the position of electron, that is bond or double bond or the negative charge, is different in all the three picture. Okay, so here what happens, if you are representing the carbonate structure of carbonate by any of these three structure, you are writing it correctly, because all these three structure are correct and will exhibit certain properties related to that particular molecule. So some polyatomic molecules can be represented by more than one structure, and all these structures which contributes to that formation, which exhibit the characteristic of that molecule, is known as canonical structure. So this is the canonical structure or resonance structure of carbonate molecule. Now instead of writing all these possible resonance structure or canonical forms, we prefer to write only one structure. For example, let's take the example of ozone molecule, O3 molecule. In picture 1 and picture 2, you can see that ozone molecule is shown, where you can see that there is transfer of double bond and charge on the oxygen atom. Now both these structures are canonical forms of the ozone molecule. It means some of the properties of the ozone can be explained by structure 1 and some can be explained by structure 2. But instead of writing these two structure, we can always write a third structure which is known as resonance hybrid, which is a structure which tries to accomplish or tries to exhibit the maximum, though it is not exhibiting the entire property of that molecule, but it can accumulate maximum properties of that molecule in that one structure. That particular structure is known as resonance hybrid. So the structure 1 and structure 2 are canonical forms, and structure 3 is what? Resonance hybrid. And it is assumed that the energy of the resonance hybrid is minimum among the all. Okay, now let's see what is resonance energy. We have seen that many polyatomic ions and molecules can be represented by different canonical forms, and each form has a different energy. Like we have seen the example of carbonate and ozone. Now energy of the resonating form is different from most stable structure, that is resonance hybrid. It means that the canonical forms of that different resonance structure will have some different energy, and their energy would be higher than the energy of that last structure resonance hybrid, which tries to exhibit most of the properties of that molecule. Now the difference in energy of the stable contributing structure and the resonating form is defined as resonance energy. It means that the energy of the hybrid minus energy of that any of the canonical forms describes the what is the resonance energy of that molecule. To summarize, it can be stated that energy of the resonance hybrid structure is less than the energy of any single canonical form. Hence, resonance stabilizes certain polyatomic molecules or ions. So, we have seen that out of all those structures, one of the structures show minimum energy, and we say that this is resonance hybrid. Okay, and that resonance of that which we observe in these molecule is observed because it minimizes the energy of the system. Next is the average of all resonating structure contributes to the overall bonding characteristic features of the molecule. All the average of that all those resonating structure will be what will contribute to the overall bonding. It will try to describe the overall bonding characteristic feature of those molecules. Okay, for example, just now we have seen the example of ozone. It can be shown by two canonical form 1 and 2, but third is the resonance hybrid, and the energy of that third is less than that of 1 and 2, and that energy is known as resonance energy. Okay, so today we have finished our chapter chemical bonding. Students, please go through these once again and you will understand it better. Allah Hafiz.